So we're going to continue our conversation about describing motion in space here. And for us to completely describe a particle moving through a space curve or on a space curve, then we need to define for ourselves three independent directions of motion. So right now all we have is our unit tangent here, but we also need to define these other two quantities, one of which is going to be the unit normal. And we'll denote that with n of t. And we're also going to define the binormal. Which will also be a unit vector. So these will give us our other independent directions, and the goal is to create three independent directions that are perpendicular to each other. That's what we really mean when we say three independent directions within R3. So we can visualize this on a space curve this way. I've pulled up a GeoGebra applet here, and you can see that we've got our tangent, our normal, and our binormal for this particular point on this curve. And that by itself is useful, but more interesting is what happens when we put this in motion and we start watching exactly how this particular point moves and twists and turns as it travels across the space curve. I think it exemplifies for us the importance of tracking these three independent directions as this point twists and turns through the space curve. We'll just change directions on it a little bit so you can see it from a different perspective. Again, traveling up along that space curve, we can see how it's twisting and turning. So pretty nice visual, again, just giving us an expectation of what it is that we're looking for and why it is important that we need this particular quantity. Okay, so let's jump back here and start defining that unit normal for ourselves. And what we're going to do is use a rule that says if you have some vector v and the magnitude of that vector is equal to a constant, then the vector dotted with its derivative is equal to 0. And this is a rule that a lot of books include, but one that we may not necessarily know right off the top of our heads, and that's okay. We're just sort of going to apply the rule here, particularly noting that the dot product being equal to 0 implies that these two vectors are orthogonal or perpendicular. To each other. So this gives us a way to now find that perpendicular vector. So if we apply this rule to our unit tangent here, what it says is if the magnitude of t is equal to a constant, and we happen to know because it's a unit vector, its magnitude is 1, then we have that t dotted with its derivative must be equal to 0. So now we have a direct way to find this perpendicular vector simply by taking the derivative of our tangent vector. So we can define our unit normal here now as simply t prime of t. But we do want it to be a unit vector, so we will divide by the magnitude of t prime. And now we have a definition for the derivative of our unit normal. So now to get that third vector, we can use our cross product rule, which we know generates another vector perpendicular to the other two, which is exactly what we need. So we can define our unit binormal here as just t cross n. So now we've got all three of these quantities defined. At this point, it's really just a matter of practicing taking these derivatives and building these particular vectors for ourselves. And the last thing we want to note is that because the magnitude of both t and n are already 1, the cross product will result in a vector that also has magnitude of 1. So some good news here is that the binormal comes out to be a unit vector anyway.